Let us start today's discussion. As we mentioned in the last class that we have to calculate. We have seen that the Hamiltonian operator for the Dirac field comes out to be of the following form: is the QT, and then we have ET summation over S, which takes the values 1 and 2. Then D dagger S T ds T minus ds T D dagger. So this was the Hamiltonian operator, and we discussed in the previous lecture that if we use commutation relations, then you can bring this D dagger on this side, on this side, and there will be a problem in the Hamiltonian because the Hamiltonian will not be positive definite. That is the biggest problem. Will not have a ground state. Therefore, the way out of this problem is to propose anti-commutation relations between the field operators, and that is of this form, and similarly for D. And if you do this, then we will see that the problem of the Hamiltonian not being positive definite gets solved immediately, because you can write this in the following form. This will be and then we can replace this by anti-commutation. Since this by definition adds a term, and there is a minus sign, therefore we have to get rid of the extra term, we have to add the dagger S. This is what we need to do, and this part is nothing but delta 3 0. It's a Dirac delta function in the momentum space, and you can see that this term gives an infinite contribution to the energy, but that term you can actually get rid by the use of normal ordering. But the problem of the Hamiltonian not being positive definite gets solved now, because now we have d dagger d plus d dagger d. So these are in number operator forms, and therefore we see that for Dirac fields we need to propose anti-commutation relations between the field, between the operators, between these operators. Once you propose this anti-commutation relation between these operators, this is the only non-trivial operator that you have, non-trivial commutation relation. Now you can calculate equal time anti-commutation relations between the Dirac field and its canonically conjugate momentum. Please do it using these commutation relations, anti-commutation relations. Please calculate the anti-commutation relation equal time between the field operator psi and its canonically conjugate momentum pi. And you will see that it satisfies the usual Dirac delta, it gives the usual Dirac delta function in the position space, but the only thing is that you have an anti-commutation relation between psi and pi. So this is all about the Hamiltonian operator. One thing, you can immediately see that from here you can see that BSP, as I mentioned, the BSP, BS and P prime anti-commutation is 0. And similarly for daggers, let's put a dagger here. This will be true. And therefore, you can, from here, what we find is that B dagger is P. This immediately leads to B dagger is P, B dagger is P is equal to 0. And similarly for P dagger. What it says is that we have already seen that B dagger is, obviously you have BSP, the vacuum is defined by in this way. BSP acting on the vacuum is 0, and similarly BSP acting on the vacuum is 0. It annihilates the vacuum. You can create particles in the following way. This will create a particle, a Dirac particle with momentum P and spin S. This is how it creates a particle. This is a creation operator. It creates a particle, an electron. It's a creation operator of an electron. It creates an electron with momentum P and spin S. Now, if you want to further create another particle in the same state, what will happen is if you act with this once more. So this is nothing but this. But from the anti-commutation relation, you know that this is 0. This is 0. What it says is that you cannot create two particles, two electrons having the same set of quantum numbers. You cannot do that, and therefore that is actually the Pauli exclusion principle. So anti-commutation relations are compatible with the Pauli exclusion principle, and therefore it is compatible with the Fermi-Dirac statistics. So that is what we mentioned in the previous discussion, that if you have anti-commutation relations, then you have spin-half particles. Spin-half particles implies anti-commutation relations, implies Fermi-Dirac statistics. So this is the connection between spin and statistics. Integral spin particles means commutation relations imply Bose-Einstein statistics, and this is also a connection between spin of the particle and statistics of the particle. So this is something important that we want to discuss. The last thing that I would want to calculate for you for the Dirac field. So we are able to quantize the Dirac field also. The only difference in case of the Dirac field from the rest of the other fields is that here we are dealing with particles having spin half, and we have to use anti-commutation relations. This is the only difference. Now, we want to calculate the charge of the total charge as we did in the case of the complex scalar field. So here also we want to do the same thing. Because if you notice carefully, the Dirac-Lagrangian density is the Dirac-Lagrangian density, and we wrote down the Dirac-Lagrangian density is I bar x, I the slash minus k, I x. If we make a transformation, just as in the case of the complex scalar field, if we make a transformation of the Dirac field in this form, where theta is a real number and is a constant, then you can immediately see from this Lagrangian density that if you make a transformation of this form, the Lagrangian density remains invariant, right? And therefore, this transformation is a symmetric transformation of this Lagrangian density, because the Lagrangian density remains invariant. And since you have a symmetric transformation like this, therefore, there will be a corresponding Noether charge corresponding to the symmetric transformation, and the Noether charge will be dq x. We shall take it to be normal ordered in this form. This immediately follows from the definition of the Noether for current density, and from there you can define the zeroth component gives you the charge density. You integrate it over the total volume V, that gives you the total Noether charge. And let us do this calculation and see what happens. It's a simple calculation. So we have done this calculation several times, and let us do it once more, and that will finish everything for the time being about the pre-quantum fields. So what we shall do here is we shall substitute the mode expansions. So for the time being, just forget about the normal ordering. We shall implement it later. So let us just write it down. You just remember that there is a normal ordering outside. So here it will be integral dq p dq prime by this is the standard factor that we always have. EP prime EP. Then we have summation S prime is psi bar x. So psi bar x, remember that this is B S prime, E prime, U bar, S prime, E prime, E to the power of I n dot x plus this will be probably B dagger, this will be B dagger, and this is B S prime, E prime, E bar, S prime, E prime, E to the power of minus I t dot x. This is the mode expansion for psi bar, and then we have psi x. Psi x is BSP, USP, e to the power of minus I t dot x plus BSP, B dagger SP, BS. So this is what psi of x is, and now we just need to plain and simple multiply these two expressions, and if you do that, we have dq prime p x. This is the standard factor that we have in front. Then it is sum s prime, and we just need to multiply. So if we do the multiplication, we shall get this term with this term gives us b dagger s prime p prime d s p u bar s prime p prime us p e to the power of I prime minus p x. The first term, let me write down the direct terms first. So there will be a plus d s prime prime d dagger s p d bar s prime prime s p the power of this will get b prime minus I p prime p x. So these are the two terms that you have, and then there will be cross terms. There will be multiplication of d with d and d dagger with d dagger. We shall not write those terms because you can, as we have shown earlier, you can show that those terms actually vanish. Those terms will be, once you do the x integral over x, those terms will vanish. So So with these two terms that we have, therefore the charge Q, that is nothing but P. You can perform the integral over x now. If you perform the integral over x, then you will get a 2 pi whole cube Dirac delta function over momentum, Dirac delta 3 p prime vector minus p vector. 2 pi whole cube will get cancelled, and you will be able to do one of the p integrals, and that will give you dq p. One of the p integral you will be able to compute, and then we shall have what? We shall have by 2 EP, then we shall have summation over S S prime P dagger S prime P, because P prime will now get changed to P because we have performed the integral over P. Then we have PSP plus we shall have P S prime P. Okay, we have missed one term here. We have missed the U's. There will be a U bar S prime P. And then we will have USP. And then we shall have plus B S prime P B dagger S P B bar S prime P B S. So this is what we should have. Okay. So this is the full expression. Now Q bar, this thing we have already used earlier, that this is nothing but 2p EP delta S prime S, and similarly this is also 2 EP delta S prime S. And from here you can see immediately that 2 EP cancels with this. There is one Kronecker delta over the spin, so we can perform one of the spins, one of the summations, and that will give us dqt summation over S. This S prime will get changed to S. So this is the expression that we get for the charge. Now remember that there is a normal order. So put the normal ordering now here, because that is how we define the charge. So the charge Q is basically the normal order form of this. So what we now do is we can just straight away use the anti-commutation relation. If you use the anti-commutation relation, then what will happen is the following. This will give you a divergent quantity, but you can throw away that divergent quantity because you have normal ordered this expression. So that divergent quantity is gone. But when you use anti-commutation relation, that adds an extra term, so you have to subtract the extra term. And thus, when you subtract it, it will become this. So what it means is that normal ordering of fermionic operators, here also you bring all the creation operators to the left hand side of the annihilation operators. But when you bring it, when you swap it, when you bring the creation operator from the right to the left of the from this position, which is to start with, it is at the right of the annihilation operator, and you bring it to the left of the annihilation operator. So you have to jump one of the fermionic operators. So these are all fermionic operators. When you jump, you get an extra minus sign. That is the only difference between normal ordering of bosonic operators and normal ordering of fermionic operators. So you bring all the creation operators to this side, but when you bring it to this side, you get a minus sign. So you just need to change this to a minus sign. So now the normal ordering operation is taken into account. So you can remove this. Normal ordering is done because you have thrown away the the divergent quantity, that divergent piece is gone, and this is your full expression for the charge, for the Noether charge. And
Sir,
here you can, yes,
so the Noether charge can be infinitely negative.
yes, it can be infinitely negative. See, these the infinite quantity that you are getting. It is basically a vacuum effect. Okay,
Yes, yes.
basically the contribution of the vacuum. The vacuum, but in quantum field theory, the vacuum is a state which contains no particles. Okay,
Hmm.
it doesn't mean that a vacuum. Since it does not contain any particle, therefore it does not mean that the vacuum has no structure. It has a lot of structure in it. Even it does not contain no particles, but the vacuum plays a very important role in quantum field theory. And you see that the vacuum has an infinite amount of energy. When we did the calculation for the Hamiltonian, the vacuum gives an infinite contribution to it has an infinite zero-point energy. And normal order basically means that you have to just throw away that infinite zero-point energy. So what you basically do is you define, just as we, in the case of potential energy, we can define the zero of the potential at any level. So here also you define the zero of energy by subtracting out the infinite contribution coming from the vacuum energy. So that is what we do. Okay.
Okay.
So now once you have normal order, your expression for the charge is this, and therefore you can now realize that B and D are really the annihilation. B and B is the annihilation operator of an electron, and D is really the annihilation operator of an antiparticle of the electron, which we name as the positron. Why? Because this number operator and this number operator, these are all number operators. This number operator contributes a charge which is E multiplied by the number of operator, and this contributes a charge which is minus E multiplied by the number operator. So it contributes a charge exactly equal and opposite to the charge contributed by the B fields. And therefore the B fields are the antiparticles. We call these as the antiparticles of this because by definition, antiparticles are those particles which have opposite charge, same spin, same mass. So these are same mass, same spin is S, but charge is opposite. And therefore, these are the antiparticles of the electrons, and these antiparticles are named as positrons. So this was the last computation involving the Dirac fields that I wanted to do. So this completes. So what we have is we have completed the quantization of all the three fields now. So our main goal now is to deal with interacting fields, interactions. So far we have been discussing free quantum fields, but now we need to proceed and discuss about interactions between these fields. We have actually discussed interactions because when you remember that when we wrote down the complex scalar field and we demanded that this field has a, instead of a global transformation, global gauge transformation, it has a local, it has a symmetry under a local transformation, local gauge transformation. So if you demand that symmetry, then you have seen that you need to bring in the electromagnetic field, and also the electromagnetic field couples with the free complex scalar field. So we get an interaction between the complex scalar field and the electromagnetic field. So we have already encountered interactions while discussing the symmetry and how to build action from gauge principle. So before going to interactions, so you know that in quantum field theory, our main aim is to explain interactions between particles. That is our main aim. The main goal of quantum field theory is to describe interactions between particles. And in this process, you want to calculate cross sections and you want to calculate decay rates. But if you want to really discuss interactions between fields or interactions between particles, so far what we have learned is that the particles that are there in nature, like electrons, photons, and many other particles, these can be considered as the quanta of a quantum field. So you take a field, quantize that field, and you get, and the particles that you get out from by quantizing that quantum field are basically the quanta of those fields. For example, in the electromagnetic case, when we quantize the electromagnetic field, we have photons as the quanta of the electromagnetic field. So now you get the real particle picture that Einstein proposed long back, that light is basically made up of packets. Now we really have a strong foundation why light is made up of packets of energy which are called quanta or particles. So you get the particle nature of light now. So you can understand how the particle picture emerges. And as I mentioned just now, that the main goal of quantum field theory is to describe interactions between particles. But in order to describe interactions between particles or interactions between fields, because fields, if you quantize, you will get the particles. If you want to describe interactions between fields, you must know how particles propagate in space and time. In space-time. So that is what is very important. We need to know how particles propagate in space-time. So we need to know what is the propagator. That is the next step that we need to do, that we need to know before discussing interactions. So let us go back to the real scalar field once again, and let us consider the following equation. Let us consider this equation. The Klein-Gordon equation in the presence of a source. And we shall be considering this equation over and over again when we do path integral quantization of fields. Then also we shall consider this equation. It's a very important thing that to consider the Klein-Gordon equation in the presence of a source J. So the question is how to solve this equation. How can we solve this equation? This is basically a partial differential equation, and you have this is an inhomogeneous partial differential equation because you have something on the right hand side. And in order to solve this equation, the standard technique is to introduce a Green's function, which I have already introduced to you, or you must have seen Green's functions in your electromagnetic theory course, in your advanced quantum mechanics course that I gave in the previous semester. We have discussed what Green's functions are, and here also, in order to solve this equation, we need to know what is the Green's function. So the standard way is to write it down in this way. The Green's function is such a function which is a function such that the operator acting on that function gives you a Dirac delta function. Okay, so this is your Green's function, and once you know the Green's function, you can immediately write down the solution of this inhomogeneous partial differential equation. So the solution will be minus x. So this is how we define the Green's function, and therefore the solution will be something like this. Where what is phi naught? Phi naught basically satisfies the homogeneous Klein-Gordon equation. By homogeneous, I mean that the right hand side is 0. So box plus n square phi naught x is equal to 0. So now you can immediately check that if you apply box plus n square, the D'Alembert operator plus n square on phi of x, then this term will be 0, and this box plus n square, it is only acting on x, therefore it will act only on g on this thing, because this is a function of x. This will give you a minus delta 4. So minus and minus will become plus. You perform the Dirac delta function, it will give you g of x. And therefore, this is indeed a solution of this inhomogeneous differential equation, partial differential PDE. This function is said to be the Green's function, and our job, so in order to get a solution of this equation, just consider this consider this as a mathematical equation, a partial differential equation, and forget about Klein-Gordon or anything. This procedure applies for any equation, differential equation that we encounter. So if we can find the form of this Green's function, then we can just put it over here. And this g of x is a known function. You give some form to it. This is a known function. So if you can find the form of this g, the solution of this partial differential equation is known. So our main aim or our main goal is to calculate this Green's function. If you can calculate this, then you know the solution to the problem. So what we do here, the standard way is a method of Fourier transform. So we write g of x minus x prime, and by the way, we could have also written this as g comma x comma x prime, but we know that this is a more general form of the function, but we notice that we have chosen it to be x minus x prime. Why? Because we know that there must be time translational invariance, there must be translational invariance, and therefore it must depend on the difference between x and difference between the 4 vectors x and x prime. So now what we do is introduce the Fourier transform, and I think I have introduced the Fourier transform. Yes, by we have d4p minus 2 pi over 4 gp e to the power of 1. This is how we introduce the Fourier transform. All the integrals are from minus infinity to plus infinity. Please remember that. And you can immediately see that box plus m square acting on this g of x minus x prime will therefore give us integral d4 pi equal 4 gp. Box acting, this operator will act only on this part because this is the part which contains x, and therefore we will get minus d square plus m square. But this is equal to the Dirac-Delta function, 4-dimensional Dirac-Delta function with a minus sign in front. Therefore, we will have the 4-dimensional Dirac-Delta function has this representation d4p in this integral representation minus I p dot x minus x prime. And now, and I have missed the e to the power of factor here. Obviously, exponential factor still remaining. Now you just compare both sides because this e to the power of this furnishes a linearly independent basis. Therefore, the only way this can be equal is the following: that gp e squared minus n squared is equal to 1. Therefore, g of p is equal to 1 by e squared. This is the only way that this can be true. And here, please remember that p mu is nothing but p0 ei, and e squared is therefore, since we are using mostly negative signature, therefore we have p0 squared minus p vector squared. And therefore, this will be equal to 1 divided by p0 squared p0 squared minus p vector squared plus m squared, and that is equal to 1 by p0 squared minus omega p squared. Here, we remember that p0 and pi, they are independent. So what we have is gp is equal to p0 square minus omega p square. So this is the form of GP, and now you know the solution to the problem, because GP you just substitute it over here. It's the form of GP. Carry out this integral over momentum p, and you know the function gx of x dx minus x prime, and therefore you know the Green's function. Once you know the Green's function, you substitute it in this equation. Therefore, you know the solution to this inhomogeneous partial differential equation. I of x is given by this, and this is phi naught is the solution to the homogeneous PD that you have. So let us stop here today at this point. I would request you to ask questions regarding the material that has been discussed so far. So we have discussed the canonical quantization of the four fields: real scalar, complex scalar, electromagnetic field in the Coulomb gauge, and the Dirac field. And we have also discussed the principle of gauge invariance and how you can build actions or build a theory by incorporating the principle of gauge invariance. And today we have just started to look at propagators. Basically, we need to know, in order to describe interactions, how particles interact among themselves or how fields interact among themselves, we need to know how particles propagate in space-time. And therefore, we need to know the propagators. And today what we have done is we have started to look at the propagator of a real scalar field. So these are the things that we have learned so far. So now you can ask questions. If you have any doubts, you can ask questions now. And another thing is that we have to take a mid-semester examination. And so when would you like to have the mid-semester examination? Please give me a date.
Sir, within what time the mid-semester examination has to be done?
The mid-semester examination has to be between 15th February to 15th March.
Sir, 25 to 30th February, maybe.
30th February?
Sorry, 28th February, yeah.
28th February?
Yeah.
So, okay, 25 to 28. Okay, so 28 is what? What is
Let me
28 is Sunday. What day? Sunday. 28 is Sunday. So 27. So what we can do is we can take the mid-semester examination on a Monday on say first March. Is it okay for you? All of you?
Okay, sir.
It is okay for you. Very good. Very good. So let us take the examination on 1st of March, and I will tell you till what point you have the syllabus, or what will be the syllabus. Okay. Let us continue for another couple of, for this week at least, and then the syllabus will be whatever we cover in this week. Is it okay, or do you want more syllabus?
No, sir, it is fine.
Okay, no. Okay, it is fine. So the syllabus, I repeat once more, the syllabus will be whatever we cover in this week. By this week, so that will be the syllabus for your mid-semester examination, and it will take place on 1st of March. So on 1st of March, all of you please, we can start the examination from what time? We can start it from, do you have classes before 10:45?
No, sir.
Okay.
No, sir.
If you have Professor Lahiri's class, so what we can do is we can start the examination from 10:10 or 10:05. Past 10 morning. Okay.
How long will it be the exam?
Around 1 hour 15 minutes or 20 minutes.
Okay, sir.
That is
Okay, from 10:05 to 11:30, say.
Sir, it will be actually a bit hard to scan and submit everything within 1 hour and 20 minutes. Because after banning of cam scanner, Adobe can take too much time
Okay.
to scan.
What you do is there is no hurry. You can scan it and send it to me later. I will just talk with the administration, and then you can send it at your own time. After your classes gets finished, you can
Within
send
Monday. Within Monday.
within Monday you send it to me.
Okay, sir. So
Okay.
it is
Okay,
like an
sir.
assignment, sir.
Within Monday you can send.
Okay, sir.
Okay, sir.
That is
Thanks.
fine. Okay.
Mm.
So let's stop here because Professor Lahiri's class is there now.
It is from 12 p.m.